Okay, so welcome everyone to this MIT Club of Rochester Tech Cafe, a special event with a guest speaker and a guest tour guide. And I will hand things over in just a moment to Dave Cameron, who's going to be our guide later, and he will introduce our speaker. I was thinking earlier, we started talking about a club event going to the Mees Observatory about 2 years ago, I think. Bob can help remember. And well before COVID. And then that we didn't get to go last year at all. And then this year we thought we might not be able to do it again, but sure enough, in the meantime, Dan Watson and his colleagues at the University of Rochester put together a remote controlled system to allow remote tours. And I've had the good fortune of seeing a couple of them as a spouse of a tour guide. So we immediately signed up for one of these evenings for the club, and here we are. But as a bonus, we recruited Dan to give us a talk about more or less behind the scenes, how this whole thing was put into operation to allow these remote tours. So with that, I will hand things over to Dave to get started and introduce Dan.
Okay, thank you, Laurel. I'm going to go to my PowerPoint, and well, first I will share my screen with everybody. So screen share. And I hope that's working. Is it working? Great. Yeah. So again, welcome. And this is the final public Mees tour of the season. Our 2001 tours, or the COVID edition. It's all new, that's for sure, but all fun and all remote. So hopefully you'll all enjoy yourselves tonight. And we have a guest speaker tonight, Dan Watson, the professor at physics and astronomy at the U of R. Before I go much farther, I'm going to be your tour guide, and hopefully if we are able to observe tonight, open up the observatory dome doors and actually look at objects in the nighttime sky, I'll be essentially driving the telescope, and that's my primary role tonight. So that's why I'm here and talking. I'll give you a brief introduction also over the next couple of minutes. But before I go any farther, I want to make sure, since this is the last tour of the season, that I take this opportunity to thank the people who made these tours possible. It starts with the staff and faculty at the University of Rochester, and especially professors Dan Watson and Kelly Douglas. And or at least my greatest thanks goes to Carol Lotta, and I don't know if she's logged in or not, but she's the tour director. And without her, there wouldn't be any tours of any type. So I'm glad that we're recording this, so this can be immortalized also. So let me get right onto the little presentation. I don't think I have to tell anybody in the club much in the way of how Zoom works. I will just reiterate that if you have any questions at any point, please don't hesitate to ask. Just unmute yourself and ask away. The idea tonight is that we can lean towards the technical with you as our tour group. So any and all questions you have, please feel free to just unmute yourself and ask at any time. And if you become logged off for any reason, just log in again to the Zoom link that was provided to you in the emails. Tonight, what we're going to be doing is this brief introduction, which is only going to be maybe another 5 minutes or so. We're then going to have the main presentation that Dan will give us, in which he'll discuss recent significant upgrades to the observatory to improve its operation, its ability to collect data, and to enable remote operation, which is a great advance, especially for the educational pursuits of students at the U of R. Then keeping all of those fingers and toes crossed, or whatever legs you break in the astronomy field to make good things happen. Hopefully we'll be able to observe live objects with the telescope. Maybe a nebula, a star cluster, a galaxy, and if it's late enough, even the planet Jupiter, perhaps. If we're not able to observe, I have pictures of all of those objects, including images taken with the Mees telescope. So we're going to be able to see them one way or another, that's for sure. And I'll certainly show you what the inside of the observatory looks like live. And again, questions, comments, discussion, it's welcome throughout the tour. The observatory itself is located in the Bristol Hills, not far from the Bristol Mountain Ski Resort, about 40 miles south of Rochester. It's at an elevation of, I think, just about 700 meters, so it's up pretty high. And these are some pictures of the grounds, grounds formerly owned by the Gannett family of the Gannett Publishing Colossus that was donated to the university years ago, and it's a wonderful site. On the site includes the Gannett House, and you can see in the picture at the top, the part of that hill that the kids go sprinting down at full speed to run around the tree and then have to climb up again. And the house is available for university departments to use for retreats. It's also used for these tours. In the bottom right is an image of a room where you would be right now, were we actually on site. You'd be sitting in that room while me or some other guides give a presentation right on that TV screen on the wall. This is the observatory itself, just up the hill from that house. Built in 1965, it features a 63 centimeter or 2-foot diameter Cassegrain reflector telescope, which you will see in a moment and throughout Dan's presentation, I'm sure. The summer tours are hosted here every year by the university, and they have been for a very long time. The telescope itself lives on the second floor of this observatory building where the red arrow is pointed. The first floor has the controlling equipment, the computers and so forth. The telescope is a flight up within that round building that we call the dome. And in a normal tour, this would be you tonight, maybe a little bit older, but maybe you'd have the same expression on your face. You'd have your eye to the telescope, and this is the telescope, what you're seeing here, this large white cylindrical object, and you'd be looking at an object up in the nighttime sky and hopefully really enjoying it. Unfortunately, COVID has come into play, and due to university regulations and policy, we're just not able to host tours on site this year. Hopefully next year we'll be able to go back. However, that doesn't mean that the tours can't be fun and enjoyable and educational too. Tonight, hopefully, we are going to observe the nighttime sky with the camera attached to the bottom of the telescope, a special digital camera. And everything, the telescope, the dome, everything is operated remotely, which we'll learn about in a moment. And we even monitor the weather on site live. We have a new weather station there. Nobody is present, as far as I know, on site tonight. There's not a human being there. It's all being done by remote control. And we're now about to learn how that has happened from Dan's talk, and I'm happy to introduce him now. Dan is the longtime mayor of Mees. I hope you don't mind me describing you as such. professor of physics and astronomy at the University of Rochester. I've written out your very brief CV, Dan. During his career, Dan has investigated the nature and formation of stars and planetary systems, spiral galaxies, active galactic nuclei, and he's also been involved in instrument development, including, or especially, instrumentation designed for infrared astronomy. He's published over 150 research publications in top journals. And tonight he's going to tell us how he, it seems almost single-handedly, I'm sure he had a lot of help, but coming from an outsider looking in, I can say Dan was the driving force on modernizing and upgrading the observatory. And I'm certainly looking forward to it. And I know this is an audience that's going to really enjoy hearing all the technical details. So I am going to stop share, although my windows have, I have to
wiggle your mouse at the bottom of your screen.
My bottom of the screen, I just have a list of, sorry, Laurel. I will turn the screen. I just have that. Oh, stop share. So I'm going to stop sharing and now take it away, Dan.
Okay. While I'm getting my share going, can everybody hear me okay? I'm seeing people nodding effusively. And now can everybody see my screen? Which, if I've succeeded, has some white lettering and pink and purple nebulae. And oh, good grief! What happened to the chat? Where's the chat box? I had it broken out just a minute ago. Hitting controls. I had chat over here. I was going to put this link in the chat. Oh, well, maybe I'll do that later if I can't find the chat, where the chat window went on my very complicated looking screen. Okay. Anyhow, a while back, Dave Cameron asked me if I wouldn't mind telling this group how one takes an observatory and makes it remotely accessible, and if possible, robotizes it. I told Dave in return that I couldn't imagine that there would be a group of people interested in hearing that, because most of the people who conduct instrumentation at that level rarely even get their close colleagues interested in sitting still and listening to what they actually did. But you know, I'm willing to make a try of it. One reason that it might be worth making a try of it is that, you know, this is a group of MIT people, and they're you have probably all been guilty of experiments from time to time. And also in astronomy these days, it's actually pretty rare for astronomers still to go to telescopes to conduct their observations. It's probably most obvious that we don't go to observatories because you see so much in the news about results from space observatories, and we can't really go there. But ground-based observatories for quite a few years now have been pretty much remote observing only. And I think it's it's been a pretty harsh reality for the latest generation of astronomers, because they don't get to go to the top of Mauna Kea in Hawaii as often as I have been there, and I've been there often enough to get bored with the place. I think it's too bad that the next generation won't get that experience, but the benefits outweigh those niggling little drawbacks, and that's why if you look around at observatories these days, you'll find that almost all of them are capable of running by remote control. Mees has been capable of running by remote control for about 2.5 years, although we didn't start to use it very continuously until the pandemic hit. The latest modifications and tweaks have made it a lot more efficient to use remotely and robotically. And if, just in case you're interested in the whole process, and in the best case, in case you have a telescope in your backyard that you were thinking of leaving up in the mountains someplace and connecting to it remotely, well, guess what? This is how you can do it. It's not really that bad. It's, it can be non-cheap, but it's something that, since it has been done at so many observatories, the parts are starting to be generally available. So I'm going to show you what we did and kind of organize it around what the most important aspects of an observatory, if it's going to be used remotely, are. And I'll keep it kind of at the top level. I haven't put performance specifications or part numbers in there, but if you want performance specifications and part numbers, just holler or put something in the chat, because I can certainly tell you what those are going to be. If you want to know more about what Mees can do and what is done, this link here that I will put in the chat as soon as I find my chat window again, is the observatory's little website, and it has a lot of presentable images and exoplanet light curves that have been taken with this telescope. The image behind the words here was also taken by this telescope, actually using the camera that is on the telescope tonight that Dave just showed a picture of. Okay. So what do you need to do to make a telescope accessible remotely? Well, first of all, you need for that telescope to have a possibility of working well enough to impress somebody with the results. And the most important thing for making impressive results is having your telescope at a good site. This applies not just to remote observing, but it applies to any observatory. An observatory, for getting good results, it needs to be dry, especially if one is doing infrared astronomy. It needs to have good weather, and it needs to be situated much higher than its surroundings. This gobbledygook on the screen in front of you is actually the primary requirement that we used to hold dear for observatories, the idea that it needs to be dark there when it's at night. This is a map of Western New York and parts of Ontario and Pennsylvania and a little bit of Ohio. I've labeled some of the features so that you can orient yourself. Lake Ontario is in the middle here. These bright white things are the big cities in Ontario and Western New York, and then further down in Pennsylvania and the megalopolis over here on the lower right-hand side. And the grayer or bluer or darker green are the dark places. And the telescope you're about to learn about is underneath this white cross here. So it's in a dark green spot. It's not quite as dark as it would be, say, up here in the Adirondacks. And I should pause to make sure everybody can see my cursor waving around here. Can you see my cursor? Okay. And not even as dark as it would be out in the middle of Lake Ontario, or in the higher parts of the Appalachians in central Pennsylvania. But it's still plenty dark. It's well outside the city lights of Rochester. And compared, one of the things that the Amateur Astronomy Club complains about to me is that their observatory is right over here on the edge of between the orange and the yellow. and they, I suppose they must be doing better these days because most of their city lights come from the nearest mall, and the nearest mall is on its last legs, it seems. So maybe this light border will retreat further north, and we'll be even in darker skies. But so we're dark, but we're in Western New York, and with Western New York weather and humidity, so we have not very many clear nights. We have not very many highly transparent nights. And we have not very many nights where the seeing, the astronomical seeing, which is the degree of blurring that the image of the star suffers due to atmospheric turbulence, all of those things are not as good as you would see in a research competitive observing site, like say a high mountain off in the middle of an ocean someplace. That's kind of the ideal condition. That's why everybody wants to build their telescopes on top of Mauna Kea in Hawaii, or on top of the high mountains in the Andes in Chile. Those are the best observatory sites in the world. And the weather's always really good in those places, and it's, as you know, not always really good in Western New York. The seeing, the blur in images is affected not just by the weather, but also by the general flow of air and what exists in the way of the air that can raise or lower the height of the turbulent boundary layer that results between the high altitude, pretty much laminar flow of air and the stuff on the surface of the Earth that can stir it up. What you don't want to have in an observatory is an observatory that is situated someplace similar to lots of other terrain around, and you certainly don't want any trees around it. So we're doing both of those things wrong. Gannett Hill, underneath the red arrow over here, is where the telescope is, and that's the highest thing around, but it's not an awful lot higher than a lot of the other hills around, especially the ones upwind over here on the left-hand side of this topo map. And as you can see in this wintertime picture of the observatory building, the trees are taller than the observatory. You see a lot of observatories built with the dome on top of a building. That's an attempt to get the telescope further away from the bad parts of the turbulent boundary layer. But it doesn't work if you've got things that are taller than that that are also making the air turbulent. So, you know, 1 for 4. The next thing that's important in—
Dan, I have a quick question.
Go right ahead.
Is the telescope pretty much out of commission all winter because of the snow that we see sitting on top of it?
It used to be hard to convince people to go up there to observe in the dead of winter, but sometimes the clear nights, especially between the middle and end of January, can be the longest and best observing nights of the year. And it was in part to gain access to those that we decided to robotize the telescope. In this picture, you can see that there's lots of snow on top, but this, let me get my cursor back over here. This shutter here folds down after this top shutter folds back, and when that top shutter folds back, it'll drag all that snow with it. Not very much snow will get into the dome, so that is okay. The dome is very slick, and it doesn't tend to accumulate very much snow. So even when you couldn't drive up the road, you could still observe with the telescope if the telescope were remotely accessible.
Yeah, I've got another quick question for you. Why don't they just cut down the trees?
We're working on that. In the direction behind where the photographer is in the wintertime picture, we've moved the tree line back quite a ways, but that was excused mostly because we couldn't otherwise see the planets in the summertime because they tend to be low in the sky and in the south. And the County of Ontario and the New York State Department of Environmental Conservation doesn't like to have large-scale felling of trees. We have a kind of touchy arrangement with the state and the county for the top of this mountain. We were given permission to use it forever so long as we give free public tours, but they still, the DEC and Ontario County, who ceded the site to the university, still need to be asked if you want to cut down a bunch of trees. So that's why we haven't done it yet. They're all hardwoods, and you figure that you could interest a lumber company in coming up there. You know, I'm sure I could make a couple of phone calls and get a lumber company to come up and take them all away for me for free, but the county and the DEC don't like it that way.
Got it. Thank you.
Okay. Yeah, please feel free to break in with questions anytime you feel like it. Second important thing, and this is perhaps the thing that would occur to you first if you're trying to remotely control a telescope, is internet. You have to have a connection that has high data rates, both upload and download. It has to have short latency, and it has to have no throttling. Throttling is what happens when, for example, in our old condition where we were getting our internet service from Verizon, they were throttling us. So after the first week or so of the month, our data rates dropped by a factor of 10 because they figured we were using too much. We have overcome that now. We used to also have an internet connection that used a satellite dish. A satellite dish relays its signals off of geosynchronous satellites at whatever that is, 84,000 feet or something like that. The forth and back delay time, and considering that you have to do 2 fourths and back for issuing a command to the telescope and then seeing with your eyes whether that command actually did what you wanted it to, is about 2 seconds. And that's way too slow to control any sophisticated piece of equipment. And all telescopes, including this one, are sophisticated pieces of equipment. So if you want to remotely control a telescope, you should try hard to get faster connections than about 10 megabits per second and shorter latency time than about 80 milliseconds. If they're slower than 10 megabits per second or more flaky than 80 milliseconds of latency, it will not be easy to control a telescope. Our connection nowadays has 60 megabits per second up, 40 megabits per second down, and usually a good deal less than 50 milliseconds latency. Our secure VPN has overheads in it that reduce our effective bandwidths to about 30 megabits per second up and down. That doesn't sound like much considering what you're probably using in your house, but it turns out to be plenty good enough for us to be controlling it remotely. All of us, even the students, have for the connections that we're sitting at back home or in the dorms or whatever, that are a good deal faster than this. So this is the limiting step in the bandwidth. But 30 megabits per second up and down and 50 millisecond latency is plenty. This has been enabled, first of all, by banning the Dish Network and Verizon from our site and getting an AT&T FirstNet wireless connection, which we have by courtesy of the fact that the University of Rochester has a medical center, and that the observatory also hosts the Western New York Mercy Flight system. We have ham radio relays and computers in our dome that relay the calls from the southern tier of Western New York through to the master system at Strong Hospital. Because we have that connection, and because AT&T has this FirstNet system that is intended for first responders wireless systems, they let us have a FirstNet wireless connection. This showed up about a year and a month ago. Next, one needs to have a robust connection, and our connection is robust as a wireless connection can be by using these dual high gain Yagi antennas. The direction of the aerials in these antennas is along the what looks like the flat side of these two enclosures, and you can probably tell from looking at this picture that those two directions are perpendicular to each other. Those are receiving perpendicular polarizations of light, or radio waves, I guess I should call them. The antennas themselves are pointed at the nearest AT&T cell tower, and that happens to be on the top of Stid Hill. Those went in the same time as this connection. By having these high gain broadband antennas in both polarizations, we can feed that to a wireless modem and a router that's capable of a 5-channel multiple input, multiple output, or if you read the tech literature on these kinds of connection, MIMO, signal aggregation. And that we've been doing actually for a year before we got this current set of hardware. That makes the connections very robust. We have very few data dropouts and very few situations in which we have had everything freeze up and couldn't communicate with the telescope anymore. So all that is good and is in the direction of safety and not destroying the equipment.
Dan, where is the tower relative to the observatory?
Oh, it's I'll be able to show you in a minute. There's a driveway right in front of the doorway to the observatory. This utility pole is on the other side of that driveway. It's 10 yards from the outside of the observatory.
Well, does it give you turbulence like trees?
It's downwind, but it's also skinnier. The wind always comes from the west in this part of the world, but it's also skinnier than the trees, so it wouldn't add to the turbulence anything like what the trees are adding. Okay, now the internet connection also needs to be secure as well as robust, and considering intruders and even worse, allowed people who lack sufficient training to run the system safely, we have a probably more sophisticated than we need, a secure VPN that's managed by our department's internal IT staff. This is one of the supreme advantages of being a techno department in a university, that we have our own internal IT staff, mostly supported by the research grants. This is good because there is absolutely no way university IT would be able to handle this. The VPN is the only portal to the telescope control computer, which I will probably abbreviate far too often in the following by TCS. All of us who hang out virtually at Mees refer to it as the TCS. Now, users with proper credentials on the VPN can use any remote desktop software tools that they want once they're on the VPN to gain access to the TCS. But the TCS, as a safety feature, only permits one user to log in at any given time. This prevents unwitting observers from issuing conflicting commands to the telescope or instruments that might either seize everything up or make the telescope run off in an undesirable direction. We haven't ever come up against the failing to tell anybody that you're trying to log into the computer and logging in and kicking somebody out and having them log back in and kick you out and go back and forth until you figure out that that must be what the problem is. But I should orchestrate something like that one of these days. Right now, Dave is logged into the TCS, and if I were to log into the TCS, I would kick him out, and he would be annoyed, and he would log back in, and he would kick me out just by virtue of logging in. But and that would be annoying, but it would keep the telescope and cameras safe. This, by the way, is what Dave is something like what Dave is looking at on one of his screens. This is the one screen of the TCS display if you shove all of the windows onto that one screen. Many of us have screens all over the place and can fill all of them with stuff from the observatory, and it's actually pretty convenient to do that these days. Okay, so internet is under good control, and I hope you've noticed that those rates and the kinds of hardware that is used here is actually not very expensive at all. Those, let me flash back here. These antennas were about $150 a pair. The modem and router were about $500. The FirstNet wireless connection is $44 a month. I guess getting permission to be FirstNet is harder than coming up with the money. So all of that is within range for just about anybody who wants to build a system kind of like this. Now, the next thing you need is, good grief, that's the wrong heading. How did I do that? Let's see. Oh yeah, I guess it is the right heading. Sorry to flip through those. I hope that didn't confuse anybody. The telescope control system itself must sound to you like a computer because I've already described it as such. And the TCS, when we call it a TCS, we're referring to this one box. But writ large, it's everything that controls the telescope. And that includes the telescope mount, the thing that swivels and allows the telescope to point in different places in the sky. It includes the enclosure, because the enclosure has to rotate around with the telescope orientation so that the telescope keeps looking out the slit in the dome rather than walking over and observing the inside of the dome. So here's what those things are like. Those are much more important than the nature and precision of the telescope that one hangs off of the mount. The mount for a remotely accessible telescope, the mount is much more important than the telescope. Usually much more expensive too. Our mount is kind of special because you can't buy them anymore. It's a Böhler and Chivens equatorial mount. Its gearing is actually precision worm and wheel gearing that was put together at Böhler and Chivens, but for those of you who have lived in Rochester and lived there for a while, the gearing was actually made at Gleason Works. So if you know what Gleason Works is and you're a mechanical engineer, you know that is the best that mechanical machining ever got. So we're benefiting from that. It's a very massive, stable system with very small periodic errors. Periodic errors are very common in things like gears that are driven by worms. This mount is vastly superior to mounts that are intended for the amateur astronomy market. And if you wanted to buy something like this today, it would cost you a few $1 million. When it was new, it cost about $300,000.
Dan, this is Dave. Can I trouble you with a rather dumb question? You mentioned that the telescope itself is on the second floor of the building.
Yeah.
Do I imagine correctly that the building itself is rather massively constructed, such that the telescope on the second floor doesn't, or rather is immune to any vibrations?
Yes, it's not that the building is massive, it's that the telescope is mounted on a reinforced concrete pier that is acoustically decoupled from the rest of the observatory building, and goes down one floor and then about one floor further down into the ground. It's about 4.5 feet square, and is just this huge, massive pillar that is very securely anchored into the ground. It goes down about 4 diameters or so into the ground. And the building was built around it, including the floor that everybody walks on next to the telescope. And you can jump up and down on the floor and not affect anything, not sense that in the encoders in the telescope. The telescope just keeps on tracking.
Right. Okay.
So
thanks.
Yeah, that is an issue, and that's a good question. Okay, anyway, this is one of the original drawings from Bowler and Chivens showing a cutaway view of the mount over here, the telescope over here, in an orientation that we forbid people to put the telescope in. Usually, you don't want this line here through the this is the right ascension axis of the telescope, and if you continue that line up to infinity, it points at the North Pole. So as the telescope tracks an object through the sky, it swivels around that axis, and it will never help to swivel the telescope all the way underneath the polar axis, and most software is booby-trapped to ever keep that from happening. So that's what the mount looks like. There's a telescope on it too. Like I said, it matters less. This happens to be a pretty special mirror. It's much better in optical quality than it needs to be, especially on this site. But it was free because one of my distinguished predecessors managed to swipe it from the NASA Stratoscope program in the early 1960s and got it put in a Bowler and Chivens tube. But we could be using a much cheaper, worse mirror and get the same results if it were the same diameter. It's an over-designed telescope primary. For those of you who do optics, its Cassegrain focal ratio is 13.5. The plate scale is about 25.1 arc seconds per millimeter. The full field of view of the telescope, what you'd see if you looked through a very wide angle eyepiece, is about 24 arc minutes in diameter. Further than that, the light suffers vignetting, a sort of soft obscuration from the parts of the telescope eventually getting in each other's way. And the effective collecting area of the telescope is about 2,700 square centimeters, including the part of the input light that's blocked by the secondary mirror. Now the mount is controlled and protected by these things. The TCS proper, the computer control system, is this thing here. It says, here's the computer and here's the drive electronics. Those two boxes of electronics are the brains of the operation. This is the scene in the control room of the observatory. There's as you can see, a couple of monitors for the computer itself, and an additional monitor for the surveillance cameras that I'll talk about in a minute. The control system operates on a standard set of telescope commands that started off in the amateur world, but is starting to be implemented in the professional world, just because there's so much cheap hardware you can get nowadays that talks this sort of hardware-specific assembly language called ASCOM. All of our control hardware and all of our cameras can talk to each other using ASCOM, and that, for example, makes automatic guiding on stars much easier than it otherwise might be. The telescope operating system also has good tools to model and refine the pointing accuracy of the telescope, which I don't do often enough. Now, all this stuff sits inside a dome that we recently replaced. All this was, I should say that the current state of the TCS is as of 2019, but we had other major upgrades in 2001, the first computerization of the telescope, and then in 2014. Also in 2014, we replaced the dome, the original dome, which had become a health hazard, with a new ash dome, this bright, shiny aluminum thing you can see here in various stages of construction before they lifted it onto the observatory itself. In the background of the lower picture here, you can see the observatory with the dome removed and a bunch of plastic keeping the rain off of the telescope. The ash dome also works with the TCS, and it automatically tracks the orientation of the telescope mount. The old dome did not do that.
Dan, you mentioned a health issue with the previous dome. Can you go into details on that?
It was painted with lead paint that was flaking off. It had a lot of joints that were soldered with solder that has mercury in it. There was a lot of other stuff around the insulators and things like that that had lots of heavy metals in them. The old dome, if we wanted to throw it away, we would have needed to break it up into a bunch of different pieces to send it off into various different Superfund sites for safe disposal. Instead of that, the Amateur Astronomy Club grabbed it, painted it, promised not to stay away from the solder joints, and now have it sitting around a telescope in Ionia. I worry about them, but we, they know what they're doing, and they at least protected all of the nasty stuff from human lungs and fingers. Okay, fourth, instruments. You don't have an eyepiece. Well, if you can put an eyepiece on the remotely controlled telescope. There is one there right now, but you won't be able to use it because you're not located there. So you need a large format camera with all the trimmings in order to make your observations, and that's a good thing because CCD cameras are far, 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 far more sensitive than eyes are. Sometimes I long for the days that all the amateur astronomy tour guides that we have will get tired of looking through the eyepiece, and they'll start to exclusively take pretty pictures with the telescope using the CCD cameras. We have good CCD cameras on this telescope that work hand in glove with the telescope control system. Now, it helps to have as much of the unvignetted field of view of the telescope full with sensitive solid state detectors as possible, and our cameras do that. We have two main cameras, one of which we bought in 2014, the other one in 2019, And they both have, as you can see in this picture down here with this colorful striations atop in front of it, that's a Kodak KAF 16803 CCD chip, 37 millimeters on the side, 4096 by 4096 pixels. That is, it's a 16 megapixel camera. And what's special about these pixels that sets it apart from the pixels in the camera in your cell phone is that the pixels are practically as wide as the pixel pitch. There are no dead spaces in this sensor. Not to mention the fact that it's got special surface treatments, special extended range for the depletion zone in the photodiodes that actually turn the light into electrons. It's just much better than commercial camera sensors and much better than eyes. They cover, with this size, a 22 arc-minute diagonal square field of view, which almost fills the telescope field of view. We wouldn't want it to be any bigger than that because the little bits of arc outside this 15.4 by 15.4 arc-minute field, we need to use to put some smaller CCDs there for automatically guiding the telescope. What we usually do during long exposures is we point the telescope where we want it, get the object on the CCD where we want it, and then we look in one of these smaller CCDs at what stars are there. And we tell the computer, okay, here's a star, issue the commands to the telescope to keep the centroid of that star's image in the same place in pixel coordinates. And it will do that. Once you tell it to do that, it will do that for as long as you want, hours and hours at a time. Auto guiding is necessary for long exposures on any telescope. You would notice the stars trailing if you took an exposure on this telescope longer than about 10 minutes. Now, each camera also has built into it an auto guider CCD, as well as this great big imaging CCD. And we also have an additional wider field off-axis auto guider and an instrument rotator. And once we went to that configuration, there is no place in the sky where we can't find a guide star that can lock our observations still. Even in star formation regions that might be dark for arc minutes and arc minutes around, we can still find suitable guide stars, although we might have to rotate the system to do so. But CCDs, like all other very sensitive detectors of light, do not sense color. One of the reasons that the CMOS sensor in your cell phone isn't as sensitive as this is that for every pixel, it actually has 3 pixels embedded in a lot of real estate with other electronics right next door. The reason for having 3 pixels right next to each other is that one of them will have a red filter glued to it, another one a green one, and another one a blue one. And all of that signal gets off and composited into an RGB image. Astronomical CCDs don't work like that. You have to take the different wavelengths at different times and then combine the images into an RGB image, if that's what you wanted to do, in software. That turns out to be easy and is worth the little bit of extra effort or automation for the extra sensitivity that you get by filling the entire focal plane with sensitive material. So to separate the wavelengths and have the camera take different colors in different exposures, you need a wheel full of filters. Here's a wheel full of square filters that can be rotated in front of the camera. The filters themselves will sit about an inch in front of the CCD chip, and they can be turned by remote control, just like everything else in the telescope can be operated by remote control. Here is that camera box again. Here's the filter wheel you just saw. Here's the offset auto guider that has a somewhat wider field of view than the one that's built into this camera. Here's a rotator that can rotate this whole assembly below it around about the optical axis. And here's a box that sticks the whole thing at the right level below the back of the telescope, and also has a remote control cover to protect the filters and the camera underneath it. This thing is camera number 2. Camera number 1 is on the telescope tonight. It doesn't look too different from this, except it doesn't have a rotator and it has an eyepiece. We have a spectrograph that we can put here too, but I'm not going to talk about that tonight because that's not one of the irreducible minimum pieces of equipment that you would want to have on your remote control telescope. So that's the instruments, and they're all remotely controllable, just like the rest of the telescope.
Dave again, back to the filters. Do you have the ability with neutral density filters to study a total eclipse of the sun?
No. To do that, we would need to wrap the telescope basically in black polyethylene. This has been done before. It's been done with big telescopes before. There's a setup at the infrared telescope facility on Mauna Kea to look at eclipses with, we actually look at the full disk of the sun with full resolution with black polyethylene. It takes about, I guess, what was that? About 30 mils of high quality, high density black polyethylene to blacken the sun enough that you can focus sunlight on a detector like this. Otherwise, you just burn a hole in it.
I see. You need one heck of a neutral density filter in order to do that.
Yeah, it's a neutral density filter that attenuates the light by a factor of about 10 to the 25th or something.
I see. Thank you.
Sure. Okay, now what happens when you put all these things together and get them working is that the first thing that will happen half an hour later is that something will break, and you wish you were there to throw the switch off and back on again. So you need surveillance. You need real-time monitoring of the conditions outside the observatory, within the observatory, and you need control over some of the things that are within the observatory at a level that is kind of may seem below the level of computer control. So let's talk about that for a minute. As you're undoubtedly aware, we have satellite weather reports surrounding us, and we have in this observatory sensors and encoders that are very good and robust, and those are all necessary, but they're not sufficient. We need local weather conditions as well, and we need visual inspection of some of the observatory's states in order for us to calm our worried minds, and also to solve problems more quickly than a drive down to Gannett Hill and drive back would accomplish. In particular, Dave will show you the weather station output later. Among the things that you need actual local weather conditions there for is relative humidity. If the relative humidity gets up to 95%, or so, the water will start condensing on the coldest thing that it can find around. Guess what the coldest thing it can find around is? It's the primary mirror of the telescope, because it's radiating to outer space. So you need, if for no other reason than to keep dew from forming on the primary mirror of the telescope, you need a weather station. Here's our weather station. You can see the anemometer and the wind vane up here at the top, and these boxes down here towards the bottom of this ellipse is the rain sensor and the electronics. And the weather station output is hardwired into the observatory because you can get wireless ones much cheaper, but the observatory building is all metal. It's a Faraday cage, so you can't get wireless signals from outside. So all of this stuff has to be hardwired, and that's why there are these conduits here that go down the pole, underneath the driveway, and into the control room.
Dan, do you ever have like mechanical problems, like the thing doesn't shut when you're open, or that kind of thing that you have to go down and take care of by hand?
But since it's happened twice this week, I guess it's not that rarely. You'll see the chief offender in a couple of slides. But we can tell that it's we can tell what's happening in part because we have surveillance. Because we have video cameras all over the place, and we can see what has happened. And we can access the video camera output not just through the observatory's computers, but those of us who deal with Mees a lot can get it on our cell phones, whether we're sitting in front of our computers or not.
But like in the winter, could you have a problem, you know, with the mechanical thing and then not be able to get there?
We could, but since the problems are rare, and the chief offender will show you would not endanger the equipment,
Okay.
it's something that we can live with so far.
Okay, thank you.
Sure. One thing about video cameras, we have 5 of them in operation right now, and one might ask, well, your camera handler can probably handle 16. Why don't you just distribute more cameras around? One reason for not doing that is that they need to see in the dark, and they see in the dark by having a ring of infrared LEDs around the outside of them. And infrared LEDs shine in the infrared, and you can think of CCDs as visible light detectors, but they're actually sensitive out to a wavelength of about 1.5 microns. So they will detect some of the broadband light from these infrared LEDs. So we try to keep the numbers of cameras within the dome down. Here's some of our surveillance. Here's 4 of the cameras of the 5 that are currently that we currently usually look at. And the 5th one you can actually see right here. It's mounted at the top of the telescope and looks at the floor so that you can see whether you've left a ladder in the way before running the telescope into it. And this illustrates the light problem. The reason that the so well here is that it's being illuminated by the ring of infrared LEDs that that comes with this particular camera. So here's a camera that's outside on that utility pole that the antenna and weather station are on. This is a view back to that. Here's a view of the lower part of the telescope where you can see camera number. Oh yeah, I took this today, so that must be camera number 1. Here's camera number 1 down here, and up at the top of the telescope, you can see the remote control telescope cover, this thing here, and both of the telescope shutters. And you can see when the telescope shutters move, you will be able to see the top shutter as it disappears past the edge of the dome slit. And you can also see in both views, this one and this one, the lower part of the shutter swing out in a way that will be obvious in a minute. Up at the top here may look like a curious thing to have around an observatory that has all these encoders and such. These are the hour angle and declination dials that are built into the telescope mount. The reason for putting a camera on them is that they are ground truth for the orientation of the telescope. they have never been dislodged or had their gears unmeshed from the telescope orientation gears since the thing was first put together. All that's happened is ordinary lubrication. So they tell us very reliably when which direction the telescope is pointing, although they don't tell us very precisely which direction the telescope is pointing. That's what the encoders are for. The easiest way to encode these dials is to point a video camera at them. So that's why that's there. It may seem clumsy, but it's cheap and very effective. Okay, 6. There are a few other things that needed to be automated, and we keep finding more and more of them as time goes on. Compare this picture with this picture, and you'll see that one of those things, that's the remote control telescope cover / flat field lamp. On the side you can't see at the moment is an electroluminescent panel that when the lid is closed like this, we can turn on and illuminate the primary mirror of the telescope uniformly with broadband light. And that is useful for taking what astronomers call flat fields, a real-time measurement of the variation in the transmission of the optics between the top of the telescope and the sensor. That's one of the things that also needed automating. It's also the thing that broke twice in the last week. But it is not broken anymore, as you can see, but by it being open here and by Dave finding it in this condition when he logged in and proceeding to close it. And that's a good illustration that often the quickest way to solve an instrument or telescope problem is to be able to see that problem happen with one's own eyes, that's the cameras, and have the ability to do something about it, like cycle the power, which I suppose comes naturally to all of us tech people. The easy, you might balk at the fact that it's not the right way to get your computer running again, but you know that cycling its power is going to bring it right back to where you started, and it's much quicker than figuring out what the problem really is. So we have to introduce a lot of things like that into the system too. We have lots of computer-controlled AC switches and uninterruptible power supplies that we can use to cycle the power to just about everything in the dome. The most frequent use is to cycle the power on the camera, the CCD camera, because it tends to latch up when it's trying to read images out very fast, and when the conduit, when the internet cables that share the conduit of the signal cables, which was a bad idea, I'm guilty of that, are doing something at the top of the telescope, that will latch the interference between those things will latch the camera up, and the only cure is to cycle the power on the camera. So there's one AC switch that you can actually see in this view here. It's that thing hanging right here, into which the camera and the CCD camera and the instrument rotator are plugged. And we can cycle the power on that. The computers, so there are lots of things around that are plugged into those computer-controlled AC switches. The router, the TCS computer itself, and the weather station are plugged into an uninterruptible power supply that we can control remotely as well and use as a smart AC switch. We can turn off various outlets on the UPS if we want to. The only thing that we can't currently turn off all the way and turn back on is the TCS. I've promoted the network modem and router to the same status as the TCS, although it doesn't need to be. It could be shut off, and we could turn it back on. But the TCS has switches in it that I would need to remove and take a soldering iron to the motherboard of the computer in order to get those switches off, and I haven't dared to do that yet. So our rule currently is that the TCS has to stay on. It has been on for a very long time. It's backed up by an uninterruptible power supply. We haven't lost power on the mountaintop in the past few years for long enough for the batteries to run down on the UPS. One reason for leaving the router in the same condition is that when we know that the power is off on the mountaintop, we can log in and shut everything else off except for the computer, and then the batteries will last longer. And finally, we have other systems like the camera cover, the telescope cover, the flat field panel, and if you want, you can wad the shutters to the dome into that, and those can all move and turn on and off under computer control. All of those things were either added or upgraded within the last couple of years.
I have a question, Dan. How many hours can the UPS provide if the power goes out, just to the TCS?
Oh, just to the TCS, about 8 hours. If everything else is plugged into it, it's more like 3.5 or 4 hours. That's why I rearranged everything so that I could basically shut everything else off. What I would do if or what I will do next time, or maybe Kelly will do it. Next time the power goes off on the mountaintop, we'll log in, shut the power off of everything else that's plugged into the UPS, and the last thing we shut off is the router itself. And that will leave just the UPS, its battery, and the TCS run. And then when the power comes back on, we'll be able to turn when the power comes back on, the router power would come back on automatically, and we'd be able to switch everything else back on by remote control. So anyway, that's what we did. So except for site quality and telescope diameter, it's worth pointing out that the observatory is outfitted very similarly and operates very similarly to large telescopes that astronomers are used to using in astronomical research. And that has a lot of good spin-offs and benefits to it. Our students are learning how to observe on a professionally outfitted observatory, to which they have an awful lot more access than they would if they needed to write observing proposals to more distant places. We don't need to travel to it anymore. So, you don't have to worry about whether you can drive up the road or not. If everything is still working, you can log in and still use a clear night. So the clear nights are used more efficiently than they were before. These days, hardly any clear sky goes to waste. Somebody is going to use it. Remote access has actually allowed us to keep all the things that we like about education and outreach in astronomy at the U of R going. It's kept our observing labs going, and now we have 5 classes that have observing experiences, including 1 graduate class, 1 advanced undergraduate lab, 2 major level astronomy courses, and new this semester, a Scopes for Dopes class that is for which the class is actually going observing remotely. I'm teaching that one. I can see Carol wincing. She's imagining how much trouble I'm getting myself into here.
Oh, I just love the name, Scopes for Dopes.
Oh, wincing at Scopes for Dopes. Okay. Carol can call it that. She has TA'd that class before. Actually, no, wait a minute. You haven't TA'd 106. You TA'd 102, right? Anyway, this group knows what I mean by that. Oops, back here. And it's the efficient operation is also getting the research groups more interested in using the telescope, mostly to take instruments that we've built on campus, either at U of R or IT, and giving them their first nighttime sky on this telescope instead of taking them off to a telescope in, say, Hawaii or Arizona or Chile, and getting there and finding out that it just doesn't work and you need to take it back to the lab and you just blew $15,000. It's much easier and cheaper to shake things down on a telescope that you can drive to in 40 minutes. So that is worth pointing out as an efficiency of the system. And there might even wind up being some research done with this telescope. I myself actually and accidentally wound up with a result a couple of years ago that turned out to be important, and I published it last summer, that involved only observations from Mees Observatory. Actually, let's see, I can even show it to you. Oh boy, is that going to take a while. Why is that taking so long? Oh, it's Zoom, that's why. It's probably going back and forth to China. Well, anyway, this is an image that I took just by way of reconnaissance. It's a picture of a very small star formation region of the sort that we call Bok globules. It has the poetic name B335, and it is home to one and only one protostar in the middle of it. And we didn't used to know how far away it was. And in fact, we still might not know how far away it was if it takes this image that long to load. We're getting down into the important region, the reason that I wanted to show it to you. Notice that in the middle of the image, it's getting darker and darker and darker and darker. And soon all the stars go away completely. And that darkness is that little molecular cloud at the center of which is precisely one protostar. You can't see it because it's behind about 300 magnitudes of extinction. But now we know, because of this image, that this globule is 164.5 parsecs away. And the reason we know that is because this bright white star here is 164.5 parsecs away. This star is surrounded by what astronomers would call a reflection nebulosity. That reflection nebulosity stretches all the way back to this Bok globule. It's part of the same collection of dust and molecular material. It used to be that our uncertainty in the distance of this globule placed it anywhere between about 60 parsecs away and 600 parsecs away, which made it kind of hard to model the protostar inside it. But when I accidentally found that I had a reflection nebula here, I knew precisely how far away it was, and suddenly all the models converged on really good fitting models for the protostar that's in the middle of that. So occasionally, even if inadvertently, a properly outfitted telescope like this that is accessible whenever you need it can do good work, even if it's not big enough to do competitive astronomy. So that went on much longer than I thought it was going to. But if you still have questions that you haven't broached, please let me know what they are. And when we get those answered, we can hand the telescope and the controls back to Dave and see if the sky is clear enough to look at stuff. It's even late enough now to look at planets.
Well, I just want to thank you for a very interesting discussion. It was really great.
Thanks. Dan, you hinted at an intruder, but we didn't see the evidence.
Oh, we haven't detected an intruder trying to break into the telescope computer yet. But in part, that's because our network security is really industrial strength.
Dave, I got a quick question for you before you go. I used to, in the not so distant past, see all these NOVA shows on telescopes and having people freezing themselves in high places because they had to be there. And in the next 5 or 10 years, are all telescopes, you know, Chile and the ones on Mauna Kea or Mauna Loa, whichever one it was there. Are they all going to go digital like this? I mean, remote like this?
They all are. During the past 5 years, practically everything has gone remotely accessible.
So we're not going to see any more pictures of freezing graduate students?
No,
Uh-oh.
not unless there's a really good reason for them to be frozen as a byproduct of the observing experience. No, most of the telescopes on Mauna Kea, for example, have been remotely accessible for 7 or 8 years. I use the IRTF on Mauna Kea quite frequently, and I haven't observed in person at the IRTF for almost 10 years.
Okay.
I've been observing only, exclusively remotely, and I like it better that way. It saves a lot of wear and tear not to have to travel to Hawaii and
Their money.
and oh yeah, there's money too. But everybody thinks that that observing in Hawaii must be a lot of fun, and the first couple of times it is a lot of fun. But after the charm wears off, and you look around and realize that you can't tell the terrain around you from the terrain on Mars, it gets old.
Okay, thank you.
So
Okay,
Dan,
Dave, all yours.
before you go, with respect to the education mission, of course, have you seen more undergraduates or even grad students at U of R using the telescope for, say, independent projects compared to, say, 5-10 years ago?
For force, I guess, yes, because now we have these independent projects in advanced labs, and those are only, let's see, those are only 2 years old. So before that, the number was 0. Now the number is like 8 per year. And I'm sure that will increase. I'm sure it will increase to the point where it becomes inconvenient to give enough time on the telescope.
Okay, and one more question. This might be a little unfair, but some of us are interested to know what's the next big upgrade that you or Kelly are going to make happen. I don't know, coffee maker or something like that down in the control.
We've got coffee makers down there, and that coffee's all going to go bad before we actually get down there to use it anymore. We're going to be, remember, well, Dave will know what I'm talking about. I'll introduce it to the rest of you as a spectrograph. We have a spectrograph that can be used with the telescope too. It's a medium to high resolution visible light spectrograph. I believe, Dave, that you were subjected to it a little bit, helping Eric put it on the telescope.
Yeah, that Shellyak.
Yeah, it's a Shellyak grating spectrograph. It's about time to get that going again, because there are a lot of good advanced lab projects that we would like to set to the students that would use that. So that's the next thing.
Okay. If there's no more questions for Dan, thanks very much. You're of course welcome to stick around for the rest of your Saturday night as I try to investigate if the weather is cleared up. There was a glom of precipitation, according to the Goes East image, that looks like it's thinning out. It was right over the telescope site. and it's according to the weather.com site, which I know is not officially approved for use, it's expanded north and south. However, that doesn't mean we can't take a look at the inside of the telescope anyway. And the longer we wait, it looks like the better things might be. Of course, people may not want to wait that long. According to telescope policy, we're not able to image Jupiter until 11:10 tonight, when it will be just at 30 degrees above the horizon. The telescope can only go so close to the horizon before problems begin to emerge that would require somebody to go to the site and fix it. And that person would probably have to be me. And so I'm not going to step on any of the telescope's toes, so to speak. However, I can show you live a little bit of the control system by sharing the screen with you. And why don't we move into that? And again, if you have any questions, yes, Dan.
I was just going to say, it looks like well, first of all, the clouds and rain are safely east of the observatory now. By the time you get around to safe observations of Jupiter, I believe it will be safe to open up.
Okay, so I'll give it about 50. Yes, thank you. The dispensation has been given by the mayor of Mees. I'll wait maybe 15, 20 minutes or so. I don't want anything going wrong, but it does look like that weather system is moving out, and maybe we will have some good luck after all tonight.
Okay. Well, I will hereby mute myself then and check in periodically to see if you need any help.
Thanks very much. I appreciate it. So let me share screen. And here you all are. And I am going to now show you, if I can, I don't know why this thing is up. Anyway, this is what I am, well, I'm trying to
You're clicking on it,
make it go away.
clicking away from it. There.
Let's see. Okay, that made it go away. Sometimes even Firefox will just decide to open up windows sometimes that are kind of strange. But what you're seeing now is the screen for the telescope control system. I have down here images of the cameras that we have on site, and you're seeing it live, and you saw this during Dan's talk. In the lower left of the images, and I can click on each of these to make it larger. It's supposed to work that way, but it didn't, but that's okay. That's the outside view of the observatory building live. The upper left is are the dials that are mounted directly to the telescope mount itself, telling you the right ascension and the hour angle. The upper right shows you the telescope itself with its lid closed, and the lower right is the bottom part of the telescope, where normally in a tour you'd be able to see people's heads right down around here, maybe standing on a ladder to look through the eyepiece that would be right around this area here. I'm going to close this for a moment and show you the output of the weather station, which gives us information about what's happening on site. Over on the upper right, we have a wind speed monitor, and We have a wind speed requirement. If it's above 12 miles per hour or so, we won't open the dome, in part because the seeing is going to be really awful in any case, but we don't want wind blowing things into the telescope. The humidity, we have an absolute don't open the dome line at about 95% humidity, because the more humid it is, that means there's a lot of water out there and maybe in the form of rain. And again, we don't want any of the equipment getting wet. And we have this available to us now. I'll see if I can reduce this guy now. There we go. And over on the right, this is the main software for the telescope control system that we use to help control the telescope and give it some background information that it needs to know in order to do its job. One of the things it needs to do is to know essentially what time it is during the day. There's a sidereal time is the phrase, and that's essentially telling you what part of the sky is on a line from the North Pole directly down to the South Pole that goes directly overhead at the zenith. What part of that sky is passing that line at this very moment? And the sky is mapped out by what we call right ascension values. And we need to tell the telescope that. Otherwise, it doesn't know what's up in the sky. And you'll see at the moment why that's important, because we have another software package that actually tells the telescope what object we want to look at and where the telescope needs to be pointed. I set this up earlier and it's a few seconds off, so I'll change it again. With a crowd like you, my MIT club friends, this is something that we normally wouldn't really spend a lot of time, or we would try not to do with the tour group present, because people are standing around and why isn't everything set up for us? We just want to look at something with the telescope. But with you, I'm a little more comfortable doing it now, in part because there's no choice, right? We had this glom of rain that was right over the observatory, and I couldn't be setting this up while Dan was giving his presentation because I can't open the dome. And secondly, because, well, maybe you'll enjoy seeing a little bit of what it takes to get the telescope to a position where we can actually use it. So let me move this guy down a little bit so you can actually see it on this screen of mine. And I have my instructions for setting up the telescope in front of me. And the first thing I would normally do is check the weather link. And we did that a moment ago, and it seems okay. Over here, I would check to make sure that the telescope is actually pointed straight up. That's information that, okay, we know you're pointed straight up. That's good. And the dials indicate that that is the case, as near as I can tell. So now we're going to set the right ascension to sidereal time. So over here in the TCS, I am going to do that. This is at 19, oh, it's about to go to 19, about 20 in a moment. I'm going to make this, oh, I can make it a little less. So once this gets to 19, whoops, I'm way off actually. So when we get to 20 and this gets to 11 seconds, I'm going to tell the telescope that that is the sidereal time. Oh, I hit it a little early, but that's okay. I'm pretty close. So I've got that done. Next, whoop, get you out of the way. Get you out of the way. All of these windows can be annoying. Let me get this down here. Come on. There we go. Next up, we need to tell the telescope at what rate you're actually tracking the sky. So I'm going to do that next here with rates. And this, I'm going to change to, this is an odd value here. It's not letting me change it. Yes, 15.03 arc second per second. Apply. And here it is down here. So I'm just going through my menu of startup that we all use to make sure that everything is done properly and in a controlled manner. The next step would be to open the dome itself. If I go back to the cameras and I especially look at this one that's looking at the outside, at night like this, it can be difficult to know if it's raining or not. Sometimes you can definitely tell, even at night. Right now, I'm not so sure I'm seeing anything coming down. Looking at the weather maps, it does look like that storm system has moved out of the way. I'm looking at two different sites. Now, it's not my telescope, so I don't want to damage it in any way. So I think we can go ahead.
Does your weather station tell you whether it's raining?
The weather station, I'll bring it up here. If the humidity, I guess, what outside humidity was super high, I guess that would tell that it's currently raining. Current rain here, I'm not so sure it's really telling me anything at the moment. Mostly we look at wind speed and the absolute humidity outside for the determinant of whether we open or not.
Thanks.
So I'm going to go ahead and open up the dome. And as you heard, Dan said, okay, yeah, I think you'll be able to do it. And independently looking at the weather maps, it seems like we're okay. Now, I don't know if it's cloudy or not directly overhead, but I don't think we have to worry too much about rain actually coming into the scope. So if I come over here to telescope and miscellaneous, this will let me open up the shutters. Recall that there are two openings in the dome. There's an upper shutter and a lower one. We have to do it in order. The first one we do is upper shutter open, and here we are, upper shutter open. I'm sorry, what was that?
Can we see the camera?
Yeah, and what I'll do is I'll switch to the camera in a second so you can actually see it open. So click this, go to the camera, and here is the upper shutter opening slowly. This takes something like 2 minutes or so. This is a very slow process, which is one reason why we don't want to open up the dome if weather is coming in. In the old days, although it was a more dangerous dome, it was a manual control. There was a big wheel that you manually cranked to open up the shutter. And if something went bad very quickly, it was pretty easy to just scramble up the ladder and close it manually very quickly. There's no quickly doing anything with these dome shutters. It's slow opening and slow closing. Of course, if something very bad happened, you could try to rotate the dome itself out of the way to try to minimize a little bit. But since we have here a little cover on top of the telescope anyway, the optics are pretty well secured. And looking at the cameras, I'm not seeing any obvious precipitation coming in, which is a good thing. One of the advantages of being there in person, it's an unambiguous way to determine if there's any precipitation going on out there or not. You just open the door and you stick your head out or your hand out and yep, that's rain. And you know you're out of luck for the night. So I'm gonna let this go for another moment. You wanna make sure the shutter is open all the way before sending the next command. And that should happen in another 30 seconds or so.
Dave, if I can just add one thing.
Yeah.
When Dan was talking about all the many advantages to having the automation now for the observatory. And by the way, I'm Carol Latta, I'm the tourist director. So it's my pleasure to sit in on your tour tonight. But one of the things that we miss a lot by not being able to be there in person is the physical experience. And right now with those shutters opening, there's some rather dramatic noise associated with that as you feel this big piece of machinery opening up. And the same thing will be true when we rotate the dome or when we slew the telescope. So there are some of those things, and that would be how we would, we would know for sure if we were there, we would be hearing that the shutter would be done as well as observing it visually. And some of those things, we really missed some of those things, like the sounds.
That's right. That would be perhaps a nice additional upgrade to make. We have a little microphone capability inside the dome that we can actually hear what it is, because the auditory cues are very diagnostic. You get to know, okay, this is the sound of the telescope moving. This is the sound of the dome or the shutters opening or closing. And you get to know those sounds. I miss them too. Okay, so that's the top one open. Now I'm going to open the lower shutter and we'll go back to the cameras to see that. This is the lower shutter here, and instead of sliding, it just kind of pivots open, and you might be able to see it here as well on the outdoor camera as that shutter comes down. The infrared light that's illuminating the inside of the dome is actually being picked up by this camera outside on the pole, so you can see it here as the shutter is slowly opening. I should also mention that immediately outside the circular room here that the telescope is within is a deck that goes all the way around this building. So not only would during a tour, would you be able to put your eye to the telescope and look at the night sky, but you could step out here onto the deck and look up yourself to do just naked eye observing or binocular observing. And sometimes the night sky is truly beautiful just with the naked eye, especially if you spend all your time in a place like Rochester or any town with a lot of light pollution. It's a nice dark spot. where the telescope is, and you can routinely see the Milky Way galaxy across the nighttime sky. And some people in our tours are seeing the Milky Way for the very first time, just by standing out here and looking with the naked eye. So there we go. There's also a neat little sound that the computer makes. It's like a little trumpet sound, like a when things are finished, like when a shutter door is done opening. I miss that too. But I think the lower shutter is now, it doesn't look like it's moving anymore. It certainly looks like it's open all the way. And now I'm going to open the dust cover that's on top of the telescope. And now you'll see it open up. And there it is, opening up for us, just as it's supposed to. I'm going to close this. Now I'm going to have my MIT Club friend help me with a calculation. It turns out that the focus mechanism, which is actually moving the secondary mirror for the telescope, is temperature sensitive. So there's a little calculation that we have available to us that if we want to set the focus, which we want to do, we need to know what the temperature is outside, and then we plug it into this little formula, which you can help me with, Laurel.
Wait, Dave, I better stop you on this.
Okay.
You've got camera number 1, not camera number 2. Camera number 2 is the one that has the well worked out temperature dependent formula. You're going to need.
Oh, okay.
You're going to need a different focus, and let me.
Thank you.
Yeah, sorry, that's my fault. I should have told you before. I'm going to look at the observing log for the most recent.
It's currently set at whatever this means. It comes up at 4056.
Okay, that is the last. That's close to the last good focus, which was 4050 at. Oh wait. Why am I not finding my own here?
What, was it at 59 degrees?
It was, okay, 4050 was the last time you observed, Carol.
Right.
I do not note a temperature in the log. It's not going to be very different from that. Start at 4050. But it's several hundred microns different from camera number 1. Sorry, camera number 2. This is camera number 1. Anyway, sorry to disrupt you there, Dave.
No, that's okay. Thank you.
Go with something like 4050 and tweak from there.
Okay, so I'm at a higher. I assume we still have that that backlash phenomenon. So I'm already starting higher.
That's right.
So if I go 40, 50 and apply, I should be in good shape. All right. Next, we open up another program called the Sky, which is over here. Ooh, ah. Okay, now let me get this in a way that I'll be able to have it make sense on one screen that can be shared, or at least try to. The first thing we need to do, this is the program that conveniently lets us, say, pick a point in the sky that we want the telescope to eventually point to. We can select it here, and then it will command the telescope to move to that point. So the first thing that we'll do here is connect the sky with the telescope control system. So I do that by hitting the connect button here. And what has happened here was you see this map of the nighttime sky. This yellow kind of bullseye has appeared. So this is where the sky thinks the telescope is pointed. The telescope is pointed directly to the zenith. At least that's what it's supposed to be pointed at right now. And so that's where it thinks it's pointed to. And it indicates that graphically right here for our convenience. Now I'm going to connect it to the camera and the rotator. So I do that over here by the camera, and it's been a little while since I've done this. And over to camera and connect. So this will initialize. This screen sharing menu. Is there any way I can make that go away? Okay. All right, so I'm just getting myself oriented here. I need to set the CCD temperature. This is a cool aspect of this camera, is that it really likes to work at low temperatures. So I do that by going to the sky camera. Temp, it may have already set itself. Temperature, excuse me while I.
Just to the right of the connect button.
Just to the right. Temp, thank you. Temp setup. It helps to have glasses on too. I'm getting to that point that, I don't accommodate to anything anymore. So the temperature set point we want is -20. I'm assuming that -20.17 doesn't make a difference. So fan on, yes. Turn off temperature regulation when the camera is different, yes. So I will say, okay. And now we will wait as the temperature goes down. See, this thing, it would be great if this whole thing could be moved away. Oh, there we go. Just gonna move it up here for now. That's it, -20. Over here on the left where my cursor is, it tells you what the current temperature actually is, and it's rapidly getting down to -20 degrees C. So we're just going to wait for that to happen before we move on.
On the map, we see Jupiter and Saturn coming up.
Yes, they're both coming up, and if we were outside, we'd go out onto the deck outside the telescope, and we'd look at them with our naked eye and maybe even with the binoculars. Saturn, unfortunately, is not far enough high in the sky for us to point the telescope to, which is really too bad, because Saturn is it's the show in the solar system, right? With that amazing ring system. But in fact, at no time, I think even in the fall, is Saturn going to get higher than 30 degrees altitude above the horizon this year. So that'll be a little disappointing for students hoping to image Saturn this year. But Jupiter will, in about 10 minutes, Jupiter will be, and here's Jupiter over here in the little map, it will get right above this blue line, and then we'll be able to try to image it.
I'm seeing like Arcturus and large, big stars, but somehow can you set it for the smaller stars? Or do you just have to head to the region of the constellation and then it opens up wider?
Oh no, you can point to any spot or any star on the sky that you wish. This is a kind of a low mag view of the entire sky. That's all. And there's lots of words that are on here. And there's Arcturus over here, and some other constellation names that people will be familiar with, like Aquarius and Pisces and all. Here is the North Star, Polaris. We're not going to be pointing anywhere near that. All sorts of problems happen when you move the telescope towards the North Pole. The software and the mechanics have a very tough time of differentiating the tiny little right ascension values and other values that you have near the North Star. And the telescope gets really wonky, and then I'll really have to make a 45-minute trip from Geneva. So there's parts of the sky that are off limits, and we just have to work within those limits. But that's okay, because there's lots of fun objects to look at. Yes, the temperature's down. Thank you.
Yeah, how does the temperature control work? How does it do the cooling? Does somebody have to crack liquid nitrogen down there or something, or is it?
That's an excellent question for Dan to answer if he's still around. I'm not sure exactly. I don't think it's a liquid nitrogen mechanism, because I don't think we have any liquid nitrogen tanks or anything like that there. So it must be some other mechanism. Maybe Carol knows. I'm not sure.
Okay, could be just a refrigerator, I suppose. Your refrigerator gets that kind of temperature.
Yeah, -20 is essentially your normal freezer in a standard at-home refrigerator. -20 is your freezer. It's not like this thing has to get down to -80 or something like that, ultra low, or anything like that. Okay, next, I'm going to click on a bright star somewhere near.
Did you say the connect rotator?
Well, connect the rotator. Excuse me, let me go back.
You said you had to connect.
Oh, no, I'm sorry. I may have spoken. Sorry about I'm seeing some of my notes that are here. And I sometimes say things out loud. So the next thing we're going to want to do to really make sure that the system knows what it's pointed at is we're going to find a relatively bright star near zenith, and we're going to have the telescope move to it. So as I look around here, and I'm just going to click here to get things out of the way, there's Vega, which is very close to zenith.
Vega's nice.
There it is, Vega. And what we'll do is we will move the telescope to Vega. We're doing that because Vega is really pretty bright. And even if we're not perfectly aligned, hopefully it's close enough to the camera that we'd be able to see it even if it's a little off axis. So we're going to keep our fingers crossed here. So there it is. Now we're going to go in the sky and we're going to move this thing out of the way again, down here someplace. And we're going to want to slew this to that object. And here's the slew command. Slewing just means moving the telescope to that position. Slew, target name Vega. Are you sure you want to slew to Vega? I'm going to click yes in a second. And if we were there tonight with everybody around, the person doing this button press would then shout slewing very loudly so that people who are upstairs know that the telescope is about to make a big move, because you don't want that telescope, it doesn't move that fast, but you don't want it to hit you in the head, because your head will, get a nice dent in it. And now the telescope represented by this yellow bullseye is moving over towards Vega. We're going to get to that. And there we go. Now it thinks it's at Vega. Now the way to know that it is to actually look to see if we're really there. So that means it's time
Oh, goody.
for the camera. So I'm going to move this guy out of the way again. And over here, I want to make sure that I have my luminance filter in place. I believe we do. Time to put the glasses back on because this is in micro print for my eyes. Filter wheel. Red, green, blue, clear. I guess clear is luminance.
And if it's not, it's 7, but you could try clear first.
Okay. I missed the first couple of words you said. Did you say that the luminance filter is filter 7?
I think that it is.
Okay. That's where it was when I opened this up. So I'm assuming that you're supposed to move it back to the luminance filter when you're done. So I'm assuming that it's there. I will move it, and it's there. Very good. And next we will take an image. So back to camera and take photo.
You're at 20 seconds.
Yeah, definitely don't want that. Actually 30. That's crazy for something as bright as Vega. So we're gonna bring this thing down to something more like half a second, I think. Got it. So 0.5 seconds. We're binning at 2 by 2, which means instead of looking at every single pixel, we're just going to kind of integrate over 2 by 2 arrays of pixels. That decreases the processing time considerably. We're not going to worry about those other things. And now we're just going to take the photo. We'll take that photo. After a moment, it will display on the screen, and we'll see whether we're actually pointed at Vega or not. Take photo. And there is Vega up here to the left. I know Vega is so bright. That's what this kind of off-axis glare is. This little dot here is not Vega, this isn't, but this thing is. It's a little off-axis, but that's not a problem. We'll be able to bring it into the view. So what I'm going to do next is get the, I have to go through my notes here to find out where the control mechanism, there we go. Pull this guy out. So I'm just going to move the telescope manually toward this direction so we can move Vega to the center of the screen. So I'm going to remove this, try to remove this. And what I'm going to do is go to the TCS Galil and go to view. Now I got to move this guy.
So everything is done by removing it and then taking another picture.
That's right. So I'm going to move it a little bit, take another picture, move, take a little picture until it's right in the center. Then we're going to confirm with the software, now you really are pointed right at Vega. And so it definitely will explicitly know what it's pointed at. So I want the star to move on the image. I want it to move to the right and down a little bit. So I'm going to press E for, first I'm going to put that for maybe 2 seconds, and then N for a couple of seconds. So 1, 2, 1, 2, and I'll stop with that. Now I'm going to take another photo. Okay, and we're getting a little bit closer. It's come down now, at least it's in the field of view. We want to get it over here a little bit. So back to the paddle controls. And I'm going to do the same thing, maybe another 2 seconds this way, maybe 3 or 4 that way. 1, 2, 1, 2, 3, 4. Now we'll go back to taking the photo. All right, we're pretty close to the middle here. So now I'm just going to move it a little bit over here some more. It's this little painstaking process is well worth the effort, because if you're not aligned right, you move the telescope to an object you want to see, and it's not in the field of view,
Right.
and you don't know what you're pointing at, and then you've got all sorts of problems. So I'm going to move it east a little bit. 1, 2, 3, 4, 5, maybe a brief bit like that. Take another photo. And of course I overshot. Not a problem. 1, 2. And we're getting very close. Maybe another half second or so.
If you wanted to use the spectroscope, would you have to visually get it in line and then use the spectroscope, or?
Oh, yeah, that you definitely need to have this aligned right on. The spectrograph has a slit that the light is coming into, and you've got to get your object right on that slit. And that can be pretty unforgiving, at least in my experience of using that thing. So this is close in the east-west dimension. I'm going to do one more little tweak to move it up slightly, and then I think we'll have this guy pegged. 1, 2. Let's see if that does it.
Uh-oh.
Odd. That's a new one.
Hmm.
Let me just close the hand paddle. Try it. Those sorts of error messages I don't like. When it's error equals, when it's a 5-digit number like that, not so good. In the interest of time, and just in the interest of time only, what I'm going to do is, although we've gone through this whole process, I don't think continually hitting this is going to clear up anything. What I'm going to do is show you some pictures that other people, and one that I've taken with this camera after going through that whole process and looking at various objects, what they would look like. And some of them are unprocessed, so it's really the way it would look like. So let me come over to this.
Oh, good.
And I'll show you the first object, or one of the first objects we would have looked at tonight was the Ring Nebula. And this is a picture of the Ring Nebula taken with that camera, or the other camera, which is very similar to it, this past April by some U of R students in one of those lab classes that Dan was talking about. A 20-second exposure with no filter, just a luminance filter. So all the light comes through. And here is the Ring Nebula, also known as Messier 57. It looks a little bit like a smoke ring in the sky, doesn't it? This is about 2,500 light years away from us, which means that the light that we're seeing from this object has been traveling through space for 2,500 years to get to us tonight. This is the former atmosphere of a star, which you can just make out in the middle of the ring, that was expelled out semi-explosively about 4,000 years ago. And if I go to the next picture I have, here's the same object color montage, so imaged with the red, green, and blue filters of the camera, and then combining those images, giving them each the color of red, green, blue, because the image itself is in grayscale. Processed a little bit, and this was taken by Dan about 6 years ago. The nebula itself hasn't changed very much in those 6 years. And here you can see some color in the smoke, what looks like a smoke ring. The red is mostly hydrogen and ionized nitrogen, all elements of different ionic characteristics emit light, absorb light at very characteristic wavelengths, and you can often identify what's there just by the spectrum. The green, it's a little hard to see the green. There's a little bit of green in there. That's ionized oxygen and so forth. This is essentially what is going to happen to our sun in about 5 billion years or so. After it expands to a red supergiant, this is going to happen, and it's not going to be well, it won't be a very good day on Earth during the red giant phase, because we'll probably be in the star's atmosphere at that point. But I don't think any of us will be around to witness it. If we are, write it down or something on the notes. So we would have looked at the Ring Nebula.
Dave?
So, yes.
Everything looks like little round circles, but if you go on a line from the nebula to the right corner, there's something that looks like a small red line. No, to the right, upper right. Like the, no, a little, in all the pictures. Okay, down, you're getting closer. To the left, to the left. To the left, right there. See, are these just a bunch of stars together? Or, because they're not like little round circles. It looks like a little line there.
I'm not seeing
Okay.
what you are.
Okay.
Here, this is a pretty good image. All the stars are these little circles here.
Right.
Everything we see here, some of these, like these very, very red ones, they may be very, very distant galaxies. I'm not seeing the red line. That might be an artifact of the image presentation, perhaps, over the internet or through Zoom or something like that. I'm not
on the other picture too.
Okay, so that might be what it is, or maybe there's something wrong with my PowerPoint that's coming through. I'm not seeing
You
it.
don't see it. Okay, thank you. Sorry.
Since the scope was pretty well pointed, I think you could safely close the sky and reopen it, reconnect and carry on if you want to image.
Okay, very good. I'll continue. I'll do that in a second. Remind me that.
Ooh.
While I'm still talking here is an image that we would never, that we would never be able to get. This is a Hubble image of the Ring Nebula, and you can see all the outstanding image quality that you can get with the Hubble. I've been told that I can maybe go back and we can try, let me try one more time, crazy thing to try.
I'm not certain if that would mess up anything with like the camera temp, but I guess you could just check that. You know, because the telescope is going to carry on. You had it on Vega, and the scope is tracking. So I think the scope is going to know where it is and do fine. And then if you reconnect to the sky after you close it and reopen it, worth a try.
I see. So close sky, which we will do.
And
Okay.
if you break it, I'm going to say it was you, not me.
Who? I'm one of those people that. No, I see your point, because the telescope is still tracking, and we did have it pointed pretty well to Vega.
Right.
So if we just close the sky, count to 10 or 5, open it again. Now let's make sure we go back and do everything just right, because
So you'll need to reconnect.
I'll need to reconnect, of course, yes. Connect. Oh yeah, that's where it thinks it is. For the camera, we want to get back to, well, first of all, let me get rid of this
Yeah, you need some more.
super long exposure time.
And I think you need to reconnect the camera, right?
Yeah.
Yeah.
Connect,
Now,
Oh, no, we didn't do it.
same error. Oh, but
Sorry.
what a good idea.
Does this
Because,
mean
yeah,
someone's driving down?
What's that?
Does the fact that this isn't working mean someone's gonna have to drive down there?
No,
No, okay.
no.
I don't think so. This sure seems like a software issue to me. But now we're getting, yeah, there's a connection issue. Let me get the camera. We'll try it one more time. I like the idea.
we're down to 2 spectators.
And otherwise, you've got some great images to show.
Yes, and I understand that a lot of people have jettisoned, and I apologize.
Just encouraging you to show great.
Okay, maybe this was long enough. Okay, it's done playing song. We connect. Camera. Connect.
Nope. Nope, sorry.
Let me make a note of the exact error.
I got it.
You got it? Okay. Thank you. The S big, so that's the camera itself. Santa Barbara imaging. Device not found. And that kicked in while we had already captured some images. All right. All right, so let me just exit the sky and go back to my little PowerPoint here for those 2 or 3 people who are still here.
10 of us.
I'm sorry, 10. Oh, okay. Well, that's nice to hear. I thought it was 2 or 3. This is another fun object. And this is what it would look like, very similar to what it would look like, even with the naked eye, to the telescope on a super dark night. This is the Hercules Globular Cluster, or Messier 13. Messier was a French astronomer back in the 1700s who was, like so many people back then, interested in hunting and discovering comets. And he kept a catalog of fuzzy objects in the sky that looked like they might be comets, but they weren't. And they knew they weren't comets because they never moved. They were always in the same part of the sky. And so he cataloged something like 104 or 105 of these objects, so that every time somebody said, "Oh, I discovered a new comet," they'd say, "No, you're seeing object number 13. It's always there. Look someplace else." So anyway, it's a very cool object, about 25,000 light years away. This is about 300,000 stars that are gravitationally associated outside the Milky Way galaxy in orbit around the galaxy. Immensely old, about 3 times as old as our solar system. And again, this picture was taken by UR students earlier this year. This light, when it first left this globular cluster 25,000 years ago, We were covered in about 3 kilometers of ice here in upstate New York. So it left, that light left that object when we were glaciated, and it's just now getting to us tonight. Here's another image taken once again by Dan Watson, an RGB true color image of Messier 13. It's a really beautiful object. You almost get a sense of 3 dimensions with it. And here, once again, the Hubble beats us all. And this is just a tiny little part of M13, imaged in visible and infrared light. And here you start to really get an idea of, okay, yeah, 300,000 stars. Now I kind of get it, and I think I believe it. These are all stars, all these little dots. Really amazing to look at.
Dave,
Another object.
Dave, before we leave that, how many light years apart are those stars? You know, are they compared to, say, the 4 light years that the North Star is from us?
Oh, they're much, much closer. The object itself, the globular cluster, is maybe about 150 light years across. So the average distance is going to be less than a light year, I think, for most of the stars that are within here. So a nighttime sky somewhere in here would be vastly different from us. You might see dozens of stars as bright as Venus, populating your entire nighttime sky. Some of them may be so close that you'd actually be able to see them in the daytime, because so many stars are packed in. There's still an appreciable distance between them. I haven't done the math to see, a volume of 75 light years radius and what the typical distance between stars, if there's 300,000 of them, but it will be a very different environment than what our sun is in, where again, the nearest neighboring star is about 4 light years away. Here, I think there'd be dozens, if not scores of stars within that distance.
Yeah, the order of, okay.
Moving farther away in space, this is the Whirlpool Galaxy, which is another beautiful object. It does look like a whirlpool. This is an image that I took earlier this summer with the Mees telescope, a 32-minute exposure. Because the light is so dim, you need that long an exposure time to really integrate and get all those photons in that you can. It's a spiral galaxy. It's not quite the same as the Milky Way, but it's kind of similar to it. This is 31 million light years away. So for 31 million years, those photons have been traveling through space to get to us. Has many star-forming regions. And you'll notice here, this bright white line, it's actually 3 lines, I believe. They're almost going right through the center of the galaxy. During this 2-minute exposure, we were photobombed, essentially, by an artificial satellite orbiting the planet that just happened to pass right through our field of view, reflecting sunlight. That's why we can see it, and almost right through the middle of what would otherwise be not that bad of an image of the galaxy. And this happens every once in a while, especially with long exposures. We have something like 18,000 artificial human-derived objects orbiting the Earth right now, the vast majority of which are junk, either dead spy satellites, dead communication satellites, rocket boosters, I think there's a couple of gloves and like nuts and bolts that are going around. And as time goes on, that's going to become more and more of a problem as these objects begin to hit each other, splinter pieces off, that collide with other functional satellites and then disable them. We're creating a junkyard in Earth orbit. And hopefully, this is the worst thing that ever happens. But it is a problem that someday needs to be addressed. Here's another image of the Whirlpool galaxy. Again, it was one of those Messier objects, number 51, taken by Dan. Again, a color image, and you can see the different colors that are here. You can see dust lanes that are in this galaxy, the dark kind of brownish bands. The red dots are areas where star formation is occurring. And this is about 300, 400 billion stars. All this, it looks like a cloud. It's not a cloud. Those are individual stars, but they're so far away from this perspective, it just looks like a smear of light, a really beautiful object. And here's the Hubble version of it, which beats everything. And here again, you can see the dust lanes, all of this little fuzz, that's all starlight. Here in red are star forming regions. This is another associated galaxy called NGC 5193, which isn't as romantic as Whirlpool. It's gravitationally associated, or at least involved, with the Whirlpool galaxy. It seems like it's tugging on this spiral arm a little bit, and there is a gravitational interaction for sure that's going on here. So this is a neat object, and we would have been able to give Jupiter a try right about now. Let me skip onto it. We were able to image some comets earlier this summer. There wasn't a good one tonight. Here's sort of what Jupiter would look like. Jupiter is honking bright. It's so bright. It's the, discounting Earth, it's the second brightest planet we can see after Venus. So bright that the Galilean moons, discovered by Galileo, of course, would be visible to the naked eye. But we can't see them because they're so close to this spotlight. They're lost in the glare of Jupiter. Anyway, this was just a 0.5 second exposure of Jupiter, and you can't really see any details in the image at all. There's no cloud bands, there's no great red spot at all. There's so much light coming in, it's saturating the camera. You can kind of tell it's saturating by the weird edge effect here. However, the idea of this project, I'm guessing, which was taken last fall, was not to image Jupiter per se, but to capture the Galilean moons and monitor their positions over several days and several weeks. So you can infer the orbital period. If you know the orbital period of these moons, you can actually, thanks to Copernicus and Newton, estimate the mass of Jupiter itself. And that's one of the projects that U of R students do in their classes. At this point, and tonight, Jupiter is about 41 light minutes away. So the Juno probe, which is in orbit around Jupiter as we speak, the scientists and the engineers that are working with that probe, they have to plan all their work and all of their computer commands such that it takes 41 minutes for the command to get to the probe. The command is implemented, and then 41 minutes to confirm that the command has been received and executed. So you have to work with this 80+ minute built-in delay for everything that you want to do. And you always have to be thinking essentially an hour and a half ahead of time for what you want to do. But they do it very well. the experts. I looked up online to figure out what were the Galilean moon's identities for that particular night and at that particular time. The Jet Propulsion Laboratory has a solar system simulator that you can access online. And sure enough, it was spot on. So that's the identity of those moons: Callisto, Ganymede, Europa, Io, which by eye, you can sometimes get a sense in the telescope of a little bit of an orangey, yellowish hue to it. And here, I'll finish with this image thanks to the Hubble Space Telescope. By eye, if we look at Jupiter through the Mees telescope, we'd be able to see these cloud bands, the central white one, this dark one sort of. I've never really gotten a convincing view of the great red spot through the Mees telescope. Perhaps you have, Carol.
I have not either. You always look for it, but it's hard to spot.
Yeah, I've never seen it, but it's there. It's shrinking apparently over the past couple of decades. It's been decreasing rather substantially in size, but it's still there. I've never seen it, but it's still a really fun object because you can make out all of these patterns on it. It's a giant planet. It's 300 times the mass of Earth. So it's the biggest.
How much time would you image?
So to image something like this was a 0.5 second exposure. So what I was hoping to do the other night, but I wasn't able to get onto the telescope, was to test some of those other filters that knock out a lot of light, like the oxygen 3 filter, the hydrogen alpha line. They're not neutral density filters, but they can kind of act as a neutral density filter, if you will, just because they only let certain parts of the visual spectrum get through. And I was going to play with some of those filters at different exposure settings to see which ones created an image that most kind of sort of looked like this, where you'd be able to see the cloud bands. I just didn't get that opportunity. And I did try to cheat by looking through the computer old photos that the students took a ways back, and none of them bothered to try to solve that problem themselves, like how to get a nice picture of Jupiter. I suspect because they had a mission: take a picture of the Galilean moons. Done. Okay, I'll go back later and do it again. They were focused and on task. They weren't interested in playing the way I would have. Good for them, I suppose. So I'm sorry that we've had this technical problem, folks. But let me go back to the telescope screen anyway, or maybe now what I'll do is I'll just go back to Zoom. So let me.
You have to close it up now, right?
Well, that's right. Well, I have to close it up anyway, and there's almost nobody left. But if you want to, end, I'm doing this just to say, if people want to say goodbye or good night, you can. I thought that's why I would do this now.
It just happened.
Thank you. Have a good night.
Yeah.
Okay, so we can do that. Back to us. I think I'm still logged in. Yeah, here I am. But my internet connection is unstable. So I'm going to go through the official. So I'm going to go through my paperwork here and get to the shutdown point. What's the problem?
I think the Zoom thing, are you still on Zoom? You see everything?
I think so. Yes, I see everybody. So I'm going to go through the official shutdown here.
If this is being recorded, is it going to be possible for us to get a link to see it or to let a friend see it?
Yes,
Yes. That usually, for some reason, that takes a long time, but we'll eventually get it.
So if we were here, we'll get a link. to-
No, it will be put on, it will be, we usually, we put, first you can get the link, send me an email note, rcars at alumni, RKARZ, as usual, alumni,
Right, yeah.
and I'll add you to the list, and then I will badger for James Hayward, who's got a lot of other things going. He'll
Uh-huh.
eventually call up whoever he calls up and get him moving, and we'll have a link. Then I'll send a link out to you, and that link is eventually going to be posted to our website. But for some reason, I do not understand. It always takes at least a week. I don't know what they're
Oh,
doing with
that's-
this thing in the meantime, but that's what it's going to take.
And it's okay to share that link with people who weren't here today.
Oh, absolutely. Yeah.
Thank you.
Okay, so send me an email. Anybody who's just, there's still 8 of us left. Anybody wants a link, send me an email saying, it was a great presentation last night. I want the link. And I'll add you to my little, I do this every month. I add you to the list. And then then I'll go badger Jim, and then I'll send an email to all of you. Okay. And it'll eventually show up on the website too.
so is it ARKARZ at,
RKARZ at alum.mit.edu.
putting it in chat for everyone. So Carol, why don't you grab that?
Yeah,
Bob's
Laurel just
email.
posted it. Thank you.
Oh,
Laurel
okay.
just put it on
So
the
you
chat.
can communicate with him directly to get that link.
Yeah, and I'll get it out to you. But as I said, for some reason or other, it takes a while, so be patient.
Okay.
Okay. The shutdown doesn't take very long, and I've already, because the sky kind of pointing program has already been shut down, I can skip a little bit. The first thing that we're going to want to do is to come over here. And we want to close the cover of our telescope. And we do that with this neat little graphic, which is a little power switch. And now we can see the cover going down.
So you won't be able to make it go point straight up. Yeah.
Yes, I will.
Or you will.
That will be done manually.
I see.
It's still pointed at Vega. We just can't get an image of it. In fact, it looked like we had it pretty well centered.
Yeah.
So covering, well, at least, silver lining. Oh yeah, we got it to point.
And there was
Oh well.
clear sky.
Yeah, it wasn't that bad. Vega's very bright, but it didn't look like it was really that obscured. You'd expect it to be pretty overwhelming, even with that short exposure time, and it was. The seeing tonight is not going to be that good. The transparency is kind of lousy because there's a lot of water vapor in the atmosphere, but we would have been able to see things, certainly. Okay, so I've got the dust cover closed. Now we're going to slew the telescope back to zenith, that is to get it pointed directly overhead. So that is telescope movement.
We can't watch it.
Yes, you can. Offset. Other stow mount at zenith. So this is going to automatically move the telescope so that it's pointing straight up. And we'll watch that. So there goes the telescope. And here's the dials telling us where it's pointed. So there it is moving. The angle of the camera kind of makes it look like it's tilted a little bit, but it's pointed straight up. As we can tell by these dials, this guy is a little, I think that's probably close enough. me get my glasses on. Yeah, that's pretty good. 42 degrees, 42, 10, 20, 30, 42 minutes. Okay. So it's pointed straight up. Now we'll send the dome home. That is, the dome itself needs to, we have a set place for it to kind of a stopping point. And we have to send it back to where it's supposed to be. Dome mode. Home. And apply. And we'll watch this, and this is always a nice loud thing. Although it's not moving.
Did you get apply depressed? Did you get the apply button depressed, Dave?
I did.
Yeah, you did.
Apply. I could do it to move dome to park position.
Can't hurt.
There it goes. Now, yeah, this will do it, I guess. Now this, every single time, except, I guess, for tonight. It usually goes all the way around in slow motion and then it stops. But it's not really at the correct position. It should be at 100.5.
Right.
Let me find home. Let me get this on so I can instantly find home. Now here it goes. That's strange.
Yeah, that was odd.
It's like it was in a local minima of some sort and it just didn't. Okay, so that's oddity number 2. Okay. For tonight. So this is that phenomena. It doesn't know to take the shortest route. All it knows is I'm going to rotate clockwise all the way around until the slit is back over here again. Apparently that's, I don't know, a ghost in the machine in the software someplace that nobody's ever been able to figure out. And if people like Dan and Kelly Douglas can't figure it out, it ain't figure outable. So we'll just wait.
While we're waiting, are you guys being affected at all by the particulates in the air from the fires in the West?
Oh,
You know, we've been getting great sunsets and stuff.
Yeah.
excellent question. I haven't been able to use the telescope at all, hardly this summer. So I don't know what the imaging, again, Dan would know. Carol might, have you noticed?
You know, I'm not, it seems like we haven't had, typically, you know, not every tour do we get to have a clear sky. I do know at the astronomy section, the local astronomy club, that there were a couple nights when any kind of observing or imaging was just kind of out of the question because it was just, the visibility was so bad because of smoke. But it wasn't as much as you would have thought. You know, it only happened for a short time. And for example, right now, it's just fine. So.
Oh, that's...
When you see those maps of the smoke, you know, we're kind of right on the edge of where the smoke is really a problem.
But like in our Buffalo map, you know, and the weather stuff, they've been putting the particulates of, you know, the and it's, you know, it gets up over 70 a bunch of times. And that seems to correlate with aggravating my lungs.
Oh, yeah.
So you actually feel it breathing, the effect
Yeah,
of
well, I
it?
have COPD. So I don't know if that's related,
Oh.
but I thought I was having allergy problems, but it didn't correlate with any pollen. But I noticed it correlated with when the particulates were high.
Hmm.
And they've been really gorgeous sunsets.
Yeah, they really have.
That's true, but causing a health problem and, oh, that's bad.
Still
Well,
not.
yeah, so it's stopped now at where it's supposed to be, so that's good. Next, we close the shutter doors in the reverse order, because mechanically they kind of fit together in such a way that we have to close the lower shutter first and then the upper shutter. And we'll monitor it with the cameras. So the first is to close the lower shutter. And again, in this camera 3, from the outside, you can see it slowly making its way up. And eventually we'll be able to see it here in camera 2 and camera 4. Maybe.
I'm not sure. Did you have to go back to dome mode of manual?
No, I didn't. No,
Okay.
it was already open. And it's, so from up here, the find home and all, and then
Yeah.
just went right down to here. It's the same,
It's coming.
subcommand. And so there it is.
Yeah, there it is.
It's slow.
So you don't normally have these type of problems on your public nights?
This is the first time it's ever happened to me.
So it looks like the MIT crew is never going to be invited back.
No,
Oh, no,
you know, this is what I've observed as a tours director. There are many little things that have to be just right to make this happen. And you notice that Dan was here for a part of the tour. For every one of the tours, we have had Dan or Kelly, the professor and assistant professor, here to back us up on operation, because there are enough little things that can go wrong. It's a very complex operation, you know, and it hasn't gotten yet to the point where you push a few buttons and it all happens just perfectly. So this is not all that untypical.
Yeah, you know, I'm sorry it happened tonight, everybody, but I'll be happy, I'm sure Carol will back me up, that when we get back to in-person tours again, one of these years, we can schedule another group outing. So you could actually be there in person. And there's nothing like being there in person, that's for sure. It's getting there.
Oh, I see the top one.
Yeah.
To me, there's a
When
visceral.
the students do this,
Yeah.
are they kind of on their own?
No, never.
Never. So there's
Well,
always some backup.
The very experienced graduate students may be on their own, but the undergraduates almost always have Kelly or Dan assisting them. Usually Kelly, because she runs most of those classes. So yeah, and there's some risk, you know, to the equipment too. So it has to be pretty carefully guided. But there are certainly students that are so experienced that they can do it on their own.
But when they're being guided, you just have 2 people online because it's not like anyone's there these days.
That's
Right.
right.
Yes.
That's right. That's why you have to be especially careful. You sometimes, if you're there and something goes wrong, well, you're there to make the fix, or the repair, or to at least make sure that nothing worse happens. When you're away, you're 45 minutes away, you have to be extra careful.
Right.
If such is possible. I'm always super careful and nervous I'm going to break something. But you definitely have to be very careful when you're far away. I'm sure the students are very responsible, but I don't know, maybe not.
Hey, you're talking to a bunch of MIT people who are all slightly OCD, so we know exactly.
Well, yeah, I mean, and that's true, and that's the way I look at it. I always think, and the guides, we needed to be trained up on this new way of doing tours as well early on. And again, this is thanks to Carol for making this actually happen. We all spent hours going through the process of what it takes to start up the telescope, to shut it down, to take images all remotely. And that took a considerable amount of time and effort from people like Carol, Dan, and Kelly. Without that, it wouldn't have happened. We wouldn't have had tours this year. And that was a lot of effort. But you still see, even with that effort, sometimes bugs happen. Sometimes the software doesn't cooperate. I don't know. I've never had that error before with the camera.
No, I haven't seen it either.
And when it happens, you're kind of stuck, especially when it's with a tour. You want people to enjoy themselves and be happy. You don't want them sitting around while you're, okay, I wouldn't do this, but okay, we're going to reboot the computer and,
Yeah.
No, here, I'll show you the fun pictures that we took earlier, kind of like a cooking show when, if the chef makes a mistake, like there's eggshells and stuff that are all in the bowl, he just tosses it away. And earlier we made, and he pulls out the ready-made cake or whatever that's already been made, and 3 hours of work is reduced down to 3 minutes. I like the tour groups to enjoy themselves and to leave with a positive impression. And so hopefully they'll come and visit us again.
I didn't realize you had all this stuff going on in Rochester, because I was part of for a while, the Buffalo Astronomical Association, and there doesn't seem to be any they had a place at Beaver Meadow, and we're doing things with the scope at the Buffalo Science Museum for, there's so much light pollution. It was mostly planets. But
the Rochester area group is very active. We have a beautiful big astronomy site with about 6 or 7 telescopes and pretty good dark skies. It's, like 20 minutes from Mees. And we operate the telescope at the planetarium and have the same light pollution issues that they do in Buffalo. Yeah. Are you Buffalo or Rochester?
I'm Buffalo.
Oh, okay. Well,
couple-
anybody who's Rochester, you should join us in the Rochester Club. It's a really active club. It's called the Astronomy section of the Rochester Academy of Science.
Okay.
And the website is rochesterastronomy.org.
Got it.
I'm going to say goodnight to everyone.